Appendix 3 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Heidi Preuss. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Commerford Martin. Appendix 3 Automatic Telegraphy. From the year 1848, when a Scotsman, Alexander Bain, first devised a scheme for rapid telegraphy by automatic methods, down to the beginning of the 70s, many other inventors had also applied themselves to the solution of this difficult problem, with only indifferent success. Cheap telegraphy being the slogan of the time, Edison became arduously interested in the subject, and, at the end of 3 years of hard work, produced an entirely successful system, a public test of which was made on December 11, 1873, when about 12,000 words were transmitted over a single wire from Washington to New York in 22½ minutes. Edison's system was commercially exploited for several years by the Automatic Telegraph Company, as related in the preceding narrative. As a premise to an explanation of the principles involved, that the transmission of telegraph messages by hand at a rate of 50 words per minute is considered a good average speed. Hence, the availability of a telegraph line, as thus operated, is limited to this capacity, except as it may be multiplied by 2 with the use of the duplex, or by 4 with the quadruplex. Increased rapidity of transmission may, however, be accomplished by automatic methods, by means of which, through the employment of suitable devices, messages may be stamped in or upon a paper tape, transmitted through automatically acting instruments, and be received at distant points in visible characters upon a similar tape, at a rate 20 or more times greater, a speed far beyond the possibilities of the human hand to transmit or the ear to receive. In Edison's system of automatic telegraphy, a paper tape was perforated with a series of round holes, so arranged and spaced as to represent Morse characters, forming the words of the message to be transmitted. This was done in a special machine of Edison's invention, called the perforator, consisting of a series of punches operated by a bank of keys, typewriter fashion. The paper tape passed over a cylinder and was kept in regular motion so as to receive the perforations in proper sequence. The perforated tape was then placed in the transmitting instrument, the essential parts of which were a metallic drum and a projecting arm carrying 2 small wheels, which by means of a spring were maintained in constant pressure on the drum. The wheels and drum were electrically connected in the line over which the message was to be sent, current being supplied by batteries in the ordinary manner. When the transmitting instrument was in operation, the perforated tape was passed over the drum in continuous progressive motion. Thus the paper passed between the drum and the 2 small wheels, and, as dry paper is a non-conductor, current was prevented from passing until a perforation was reached. As the paper passed along, the wheels dropped into the perforations, making momentary contacts with the drum beneath, and causing momentary impulses of current to be transmitted over the line in the same way that they would be produced by the manipulation of the telegraph key, but with much greater rapidity. The perforations being so arranged as to regulate the length of the contact, the result would be the transmission of long and short impulses corresponding with the dots and dashes of the Morse alphabet. The receiving instrument at the other end of the line was constructed upon much the same general lines as the transmitter, consisting of a metallic drum and reels for the paper tape. Instead of the 2 small contact wheels, however, a projecting arm carried an iron pin or stylus, so arranged that its point would normally impinge upon the periphery of the drum. The iron pin and the drum were respectively connected so as to be in circuit with the transmission line and batteries. As the principle involved in the receiving operation was electrochemical decomposition, the paper tape upon which the incoming message was to be received was moistened with a chemical solution readily decomposable by the electric current. This paper, while still in a damp condition, was passed between the drum and the stylus in continuous progressive motion. When an electrical impulse came over the line from the transmitting end, current passed through the moistened paper from the iron pin, causing chemical decomposition, by reason of which the iron would be attacked and would mark a line on the paper. Such a line would be long or short, according to the duration of the electrical impulse. Inasmuch as a succession of such impulses coming over the line owed their origin to the perforations in the transmitting tape, it followed that the resulting marks upon the receiving tape would correspond thereto in their respective lengths. Hence, the transmitted message was received on the tape in visible dots and dashes representing characters of the Morse alphabet. The system will, perhaps, be better understood by reference to the following diagrammatic sketch of its general principles. Some idea of the rapidity of automatic telegraphy may be obtained when we consider the fact that with the use of Edison's system in the early 70s, it was common practice to transmit and receive from 3,000 or 4,000 words a minute over a single line between New York and Philadelphia. This system was exploited through the use of a moderately paid clerical force. In practice there was employed such a number of perforating machines as the exigency of business demanded. Each machine was operated by a clerk, who translated the message into telegraphic characters and prepared the transmitting tape by punching the necessary perforations therein. An expert clerk could perforate such a tape at the rate of 50 to 60 words per minute. At the receiving end, the tape was taken by other clerks who translated the Morse characters into ordinary words, which were written on message blanks for delivery to persons for whom the messages were intended. This latter operation, copying as it was called, was not consistent with truly economical business practice. Edison therefore undertook the task of devising an improved system whereby the message, when received, would not require translation and rewriting, but would automatically appear on the tape in plain letters and words, ready for instant delivery. The result was his automatic Roman letter system, the basis for which included the above-named general principles of perforated transmission tape and electrochemical decomposition. Instead of punching Morse characters in the transmission tape, however, it was perforated with a series of small round holes forming Roman letters. The verticals of these letters were originally 5 holes high. The transmitting instrument had 5 small wheels or rollers instead of 2, for making contacts through the perforations and causing short electrical impulses to pass over the lines. At first, 5 lines were used to carry these impulses to the receiving instrument, where there were 5 iron pins impinging on the drum. By means of these pins, the chemically prepared tape was marked with dots corresponding to the impulses as received, leaving upon it a legible record of the letters and words transmitted. For the purposes of economy and investment and maintenance, Edison devised subsequently a plan by which the number of conducting lines was reduced to 2 instead of 5. The verticals of the letters were perforated only 4 holes high, and the 4 rollers were arranged in pairs, one pair being slightly in advance of the other. There were, of course, only 4 pins at the receiving instrument. 2 were of iron and 2 of tellurium. It being the gist of Edison's plan to effect the marking of the chemical paper by one metal with a positive current and by the other metal with a negative current. In the following diagram, which shows the theory of this arrangement, it will be seen that both the transmitting rollers and the receiving pins are arranged in pairs, one pair in each case being slightly in advance of the other. Of these receiving pins, one pair, 1 and 3, are of iron, and the other pair, 2 and 4, are of tellurium. Pins 1, 2, and 3, 4 are electrically connected together in other pairs, and then each of these pairs is connected with one of the main lines that runs respectively to the middle of the groups of batteries at the transmitting end. The terminals of these groups of batteries are connected respectively to the 4 rollers which impinge upon the transmitting drum, the negatives being connected to 5 and 7, and the positives to 6 and 8, as denoted by the letters N and P. The transmitting and receiving drums are respectively connected to earth. In operation, the perforated tape is placed on the transmission drum and the chemically prepared tape on the receiving drum. As the perforated tape passes over the transmission drum, the advance rollers 6 or 8 first close the circuit through the perforations, and a positive current passes from the batteries through the drum and down to the ground, thence through the earth at the receiving end up to the other drum and back to the batteries via the tellurium pins 2 or 4 and the line wire. With this positive current, the tellurium pins make marks upon the paper tape, but the iron pins make no mark. In the merest fraction of a second, as the perforated paper continues to pass over the transmission drum, rollers 5 or 7 close the circuit through other perforations, and current passes in the opposite direction, over the line wire, through pins 1 or 3, and return through the earth. In this case the iron pins mark the paper tape, but the tellurium pins make no mark. It will be obvious, therefore, that as the rollers are set so as to allow of currents of opposite polarity to be alternately and rapidly sent by means of the perforations, the marks upon the tape at the receiving station will occupy their proper relative positions, and the aggregate result will be letters corresponding to those perforated in the transmission tape. Edison subsequently made further improvements in this direction, by which he reduced the number of conducting wires to 1, but the principles involved were analogous to the one just described. This Roman letter system was in use for several years on lines between New York, Philadelphia, and Washington, and was so efficient that a speed of 3,000 words a minute was attained on the line between the first 2 named cities. Inasmuch as there were several proposed systems of rapid automatic telegraphy in existence at the time Edison entered the field, but none of them in practical commercial use, it becomes a matter of interest to inquire wherein they were deficient, and what constituted the elements of Edison's success. The chief difficulties in transmission of Morse characters had been 2 in number, the most serious of which was that on the receiving tape the characters would be prolonged and run into one another, forming a draggled line, and thus rendering the message unintelligible. This arose from the fact that on account of the rapid succession of electric impulses there was not sufficient time between them for the electric action to cease entirely. Consequently the line would not clear itself and become surcharged, as it were, the effect being an attenuated prolongation of each impulse as manifested in a weaker continuation of the mark on the tape, thus making the whole message indistinct. These secondary marks were called tailings. For many years electricians had tried in vain to overcome this difficulty. Edison devoted a great deal of thought and energy to the question, in the course of which he experimented through 120 consecutive nights in the year of 1873 on the line between New York and Washington. His solution of the problem was simple but effectual. It involved the principle of inductive compensation. In a shunt circuit with the receiving instrument he introduced electromagnets. The pulsations of the current pass through the helices of these magnets, producing an augmented marking effect upon the receiving tape. But upon the breaking of the current, the magnet, in discharging itself of the induced magnetism, would set up momentarily a countercurrent of opposite polarity. This neutralized the tailing effect by clearing the line between pulsations, thus allowing the telegraphic characters to be clearly and distinctly outlined upon the tape. Further elaboration of this method was made later by the addition of rheostats, condensers, and local opposition batteries on long lines. The other difficulty above referenced to was one that had also occupied considerable thought and attention of many workers in the field, and related to the perforating of the dash in the transmission tape. It involved mechanical complications that seemed to be insurmountable, and up to the time Edison invented his perforating machine, no really good method was available. He abandoned the attempt to cut dashes as such in the paper tape, but instead punched 3 round holes, so arranged as to form a triangle. A concrete example is presented in the illustration below, which shows a piece of tape with perforations representing the word "same." The philosophy of this will at once be perceived when it is remembered that the 2 wheels running upon the drum of the transmitting instrument were situated side by side, corresponding in distance to the 2 rows of holes. When a triangle of 3 holes, intended to form the dash, reached the wheels, one of them dropped into a lower hole. Before it could get out, the other wheel dropped into the hole at the apex of the triangle, thus continuing the connection, which was still further prolonged by the first wheel dropping into the 3rd hole. Thus an extended contact was made, which, by transmitting a long impulse, resulted in the marking of a dash upon the receiving tape. This method was in successful commercial use for some time in the early 70s, giving a speed of from 3,000 to 4,000 words a minute over a single line, but later on was superseded by Edison's Roman letter system above referred to. The subject of automatic telegraphy received a vast amount of attention from inventors at the time it was in vogue. None was more earnest or indefatigable than Edison, who during the progress of his inventions took out 38 patents on various inventions relating thereto, some of them covering chemical solutions for the receiving paper. This of itself was a subject of much importance, and a vast amount of research and labor was expended upon it. In the laboratory notebooks there are recorded thousands of experiments, showing that Edison's investigations not only included an enormous number of chemical salts and compounds, but also an exhaustive variety of plants, flowers, roots, herbs, and barks. It seems inexplicable at first view that a system of telegraphy sufficiently rapid and economical to be practically available for important business correspondence should have fallen into disuse. This, however, is made clear, so far as concerns Edison's inventions at any rate, in Chapter 8 of the preceding narrative. End Appendix 3.